Apparent weight in lifts. Your weight is due to the gravitational field of the Earth exerting an attractive force on you. We can calculate this force using the equation weight in newtons is equal to your mass in kilograms multiplied by the gravitational field strength in newtons per kilogram, or W equals mg. On Earth, the gravitational field strength is 9.81 newtons per kilogram, or we can quote it as 9.81 meters per second squared. These two different units are equivalent, and we would generally use these units when considering forces and these units when considering the motion caused by these forces. This weight does not change when you go up or down in a lift, but you will have experienced feeling lighter when the lift starts going down and feeling heavier when the lift starts going up. We judge our weight by the reaction force of the ground on our feet and the pull of our internal organs on our body. Both of these forces change when accelerating in a lift, so we feel a different weight. We have an apparent weight change. Here we have a person in a lift. There will be their weight, W, acting down, which is equal to their mass times the gravitational field strength, and there will be the reaction force, R, acting up. When the lift is stationary or moving at a constant speed, i.e. there is no acceleration, the reaction force will equal the weight of the man. So we can say that R is equal to mg. When the lift is accelerating down, there must be a resultant force down. If we take down as positive, the resultant force will equal the weight, which is already acting down in the positive direction, plus minus the reaction force. As the reaction force is acting up, it acts in the negative direction. So we can write that the resultant force, which will cause the acceleration of the man, ma, is equal to mg, the weight, minus the reaction force. We can rearrange this as the reaction force is equal to mg, the weight, minus ma, the resultant force, which is equal to mg minus a. You feel lighter. When the lift is accelerating up, there must be a resultant force up. So if we now take up as the positive direction, we can say that the resultant force will be equal to the reaction force, which is acting upwards in the positive direction, plus the minus of the weight, as the weight is acting in the negative direction. So we can write this as the resultant force, ma, is equal to the reaction force minus the weight. We can rearrange this as reaction force is equal to weight plus the resultant force, which is mg plus a. You feel heavier. Let's look at an example. A 75 kilogram man accelerates down in a lift at 2.5 meters per second squared. Calculate his apparent weight. Well, now reaction force, or apparent weight, is equal to mg minus a, which is his mass 75 kilograms, gravitational field strength, and the acceleration, giving a reaction force, or apparent weight, of 548 newtons. The lift then continues down at a constant speed of 3 meters per second. What is his apparent weight now? Well, with no acceleration, this is just his actual weight, which is given by mass times gravitational field strength, a value of 736 newtons. The lift then decelerates at 1.5 meters per second squared. Calculate his apparent weight now. Well, for this we need reaction force, or apparent weight, equals mg plus a, and putting in the figures gives him an apparent weight of 848 newtons. When a parachutist first jumps out of the aeroplane, the only force acting on them is their weight. This then is their resultant force. So mg is equal to ma. They still have the same weight as before, but they appear weightless. Astronauts in orbit around the Earth still have weight, but they are constantly in free fall towards the Earth, and so have apparent weightlessness. They train for these conditions in the back of large aircraft as they accelerate towards the Earth, creating apparent weightlessness for a short time. The only way to have true weightlessness is to go into outer space, a very long way away from any other objects.